So what we wanted to do is be able to anticipate the line emission of the CME from the different plasma components of the CME, the prominence and adjacent structure as it accelerates and expands in the corona. And we not only want to look for lines that are bright, but we also want to anticipate which ions will remain in ionization equilibrium throughout the evolution that we're considering. We're actually looking out to about 2 solar radii, or we're testing lines out to that height. And of course, we want to know which future instruments will be capable of observing some of those lines that might be useful. So like I mentioned in the abstract, this work focuses on observations from DKIST, UCOMP, and SPICE on Solar Orbiter, but of course these lines have probably been observed by other instruments, current and past instruments as well. So as most of you probably already know, DKIST is only looking at a pretty small portion of the sun with some off-limb capabilities. So I actually stole this from one of the DKIST workshops, the presentations from the DKIST workshops that I was at. But this is approximately 4 arc minutes, and this is the field of view, all the different instruments on DKIST. So it's a very small portion of the sun. While UCOMP, so UCOMP is the upgraded version to COMP, if you're familiar with COMP. So both of these instruments are looking at the visible and near infrared. But with COMP, we're actually going to the field of view is going to be expanded out to 2 solar radii. So together, if you're lucky and happen to capture a CME with both these instruments, you may be able to study the release and also the evolution out to a couple solar radii from the surface. And of course, SPICE is looking in the EUV, so it's looking at 2 EUV wave bands, and it's an imaging spectrometer, so with a slit length of about 13 arc minutes and a scan range of about plus or minus 8 arc minutes, which is slightly bigger than what DKIST is gonna look at. But there are also lines in the list that we looked at that aren't going to be observed by these instruments. And those lines are still important because they can be useful for people to design future instruments for observing CMEs. So the synthetic intensities, we generated synthetic intensities along the line of sight, integrated along the line of sight as a function of distance from the sun. So we looked at roughly about 1.05 solar radii out to 2 solar radii, which is the edge of UCOMP. We figured that'd be a really good distance to look at. And the intensities are governed by collisional excitation and radiative scattering, and we use atomic data from Chianti. So for those of you that may not know what collisional excitation looks like, or just need a reminder, so this is a cartoon picture I made. And essentially, collisional excitation involves a free electron in the plasma that then collides with your atom, which can then bump up your electron up to an excited state. If in the absence of any other collisions or anything else, then the electron can come back down and you get a photon. So in this case, the intensity is a very strong function of the electron density. And then radiative scattering is simply, in this case, you have a photon that gets absorbed by the atom and then again re-emitted in a different direction. So in this case, the intensity is a function of the incident flux and a couple of other things, but it scales linearly with density. It's just something to keep in mind. All right, so also for composition, so I haven't mentioned this before, but I sort of hinted at it or I think I said it in the abstract. We're using a previously studied reconstructed CME to generate these intensities. And that CME, that model of the CME, contains different components. So it contains the evolution of a prominence eruption and the adjacent structures, the warmer structures. And so what we've done is we've specified photospheric abundances for the prominence material and then coronal abundances for the rest of the CME, which is something that's typically seen in observations. So we wanted to differentiate between the two. Okay, so relative abundances. So we also, in order to calculate the contribution function and the number of absorbers, we need to specify relative abundances as a function of distance. So throughout the evolution of the plasma of the different structures. So in order to account for non-equilibrium effects that may arise from the dynamic nature of the eruption, we calculate the relative abundances of the different ions with the Michigan ionization code of the different structures. So this is just an example, an output, I think, for the prominence material. So these are all the charge states of carbon up here. So relative abundance as a function of distance. And this is for iron. So you can see how they're changing. So this is much farther than we're actually looking. It's out to 15 solar radii. But you can see that even at the distance that we're at, there's still a lot of change happening in some of the plasma. And so we model the CME. We have very simple geometry for the CME. So this is the top view of the ecliptic plane. This is the sun here, and then the CME moving away from the sun. So what we do is we specify a particular angular width for the different structures of the CME that, as it moves away from the sun, subtends a constant angle as it's self-similarly expanding. And we also specify a filling factor for each plasma structure. So the filling factor is really important because it could be very different than one, especially for the prominence material. It can vary. People have shown that it could vary or have calculated a variation of several orders of magnitude. So that's very important. I think we use a value of about 0.1. But since it scales linearly with intensity, you can sort of, for the intensities that we calculate, if you wanted to use a different filling factor, you could just eyeball it because it would linearly scale. So it's very useful. So how we chose the different lines that we tested, we went about it a couple of different ways. So what we did is we calculated spectra using Chianti, using a previously studied filament core. And so we've generated the spectra, and we look through between the EUV and the near infrared for prominent lines that might be useful to look at. And we also included, of course, specific lines for the instruments on DKIST, as well as some of the lines that were highlighted under the scientific goals of SPICE. And of course, we included all the lines for all 9 lines of UComp. We tested with all the different components. So this is one of 3 tables that we included in the paper. So there's about a third of the lines, just to give you a sense of what we've included. So we have information about the line, but we also have a column where it tells you which line is going to be observed by which instrument, which I think is very useful and was very, very tedious to do. But this is, there were a total of 118 lines that we looked at that ranged between 100 to about just over 14,000 angstroms to encompass the entire range. That were had a formation temperature about from 10,000 to just over 5 million Kelvin to really look at the evolution and the heating in the plasma. Let's see. So, like I mentioned, we used we took the evolution, the density, temperature, and velocity profiles from a previous paper. And here, the different components that were included in that study contain, so prominence material that's very, very dense and relatively cooler than the other components. There's also 2 prominence to coronal transition region lines or profiles, different plasma components in the red and the yellow. So the PCTR tends to be a little warmer than generally warmer than the prominence core and slightly more dense. It looks, in this case, a lot more dense, or less dense. And that typically surrounds the much cooler core. And then we have this 4th plasma here. So in the blue, this is coronal type plasma, just a hotter component of the CME. And so the way that we model these different components are as convective layers surrounding the prominence material. So you have here the core, and then the two PCTRs, and then the coronal plasma around that. And this is a very idealistic, typical picture of a filament material on the surface of the sun. That's sort of in this contained within the magnetic topology, which is typically a flux rope. So this CME was reconstructed. Yeah.
The ionization equilibrium that you compute includes photoionization from the coronal plasma.
Yeah.
3 most radiation.
Mm-hmm.
Okay.
Yeah.
That could dominate.
Yeah, definitely. So this is Enrico. If you know Enrico Landi, so he is he actually that's the last thing that he added to the code. So it does include photoionization, and it does become important. So
Also, the ionization balance driven by photons.
Right.
Okay.
So
Question as well. So I'm not sure if I understand what's going on here with this picture. So the red and yellow parts are heating up as the CME expands or comes out, but the blue part isn't. Why? What's the reason for that?
There's no yeah. So the blue component is mainly just cooling. There was no, well, it's not. It's not. So it's not. If I were to post the like adiabatically expanding profiles up here, it's still being heated, but the temperature isn't going up. The electron temperature isn't going up because there's also expansion happening. So there's there's sort of a competition between the two, but it is heating. Okay, so this CME that we reconstructed we reconstructed with measurements in the heliosphere. However, those measurements in the heliosphere are also linked to an eruption back at the sun. So I wanted to show you what that eruption looks like to give you a sense of what type of CME we were reconstructing. So there's actually two CMEs going on here, but so it's this one here. So there's a huge filament here, and so the measurements that we see in situ are from this huge filament eruption that happened in 2005. So it drove this halo CME directed towards the Earth, and it had an average acceleration of about 15 kilometers per second, and it reached the leading edge reached about 900 kilometers per second at 30 solar radii.
Acceleration is kilometers per second squared.
Yes. Oh. Thank you. Mm-hmm. So I think this is the average. That might have been, so this is coming from the LASCO. No, it was 15. I can show you. Yeah, but it might not, so it might not be, I'll take another look. I'll show you where I was looking. Because it was done with essentially following the leading edge, and then a fit done to the velocity.
Like 7 or something was the peak ever seen in the past. So, okay.
Maybe. I'll take a look at that. And so here, so this CME is also associated with B-class flares. So not a very strong flare, so not a very energetic event. Okay, so these are the intensities that we've generated. So these are the results. These are the intensities that we generated for the prominence material. So the core, the filament core, we set to an angular width of 30 degrees and a filling factor of 0.1. And these are just intensity of the different lines that we tested as a function distance, so out to 2 solar radii. Here are there are a ton of lines, but here I'm showing some lines in the EUV, and then in the visible and infrared. So generally what we find is that the prominence material generated the brightest and likely the most observable lines of all the different components that we looked at. We expect the lines to decrease as a function of distance because the plasma is expanding, the density is decreasing really quickly. What's interesting is that a lot of the lines are decreasing at their specific rate, right? They're not all decreasing in the same way, which is not terribly intuitive. So this is something something that where the study becomes really valuable, where you have the opportunity to sort of compare the different lines evolving within this type of plasma in order to get a better sense of which lines would be the most bright. Even out to 2 solar radii, there's lines that are very bright at the surface but can also maintain a pretty significant signal out to here, all of which most of the lines in the prominence material can maintain ionization equilibrium out to that height. And so when we look at some of the plasma from the PCTR, so for this plasma, we set an angular width of, so it should be 3 degrees. This is an anger, yeah. And a filling factor the same as the prominence material. So in this case, what we find is a lot of the lines tend to become bright and then immediately dim. So there's only a small stage during the evolution where these lines become bright. And so these intensities sort of follow the creation and ionization of the emitting ion. So if you look at the plot, so this is intensity as a function of distance. This is a plot showing the intensities, all the intensities that we generated for iron. Intensity as a function of distance for both non-equilibrium intensity, so it's these lines, versus the equilibrium intensities using the values that would be generated with ionization equilibrium. And then below that are the relative abundances. So the non-equilibrium relative abundances of the different charge states of iron evolving within that plasma. So this is for the PCTR, so plasma. And so one thing that you'll notice immediately is that this plasma is ionizing very, very quickly. So it's going through these ionization stages very quickly. And if you look and you compare the non-equilibrium and equilibrium intensities that are generated by these lines, you can very quickly see that the ions are perpetually out of equilibrium because this is happening so quickly. And this is true not just for the iron ions that I'm showing here, but most of the ions in the PCTR are out of equilibrium.
Out of equilibrium, that's the polar ions.
Right, so it just depends on, right, how they compare. And so for completeness, I just wanted to show you the coronal plasma. So in this case, these intensities for the coronal plasma look very similar to what we see for the prominence material, except here they're a lot less intense, they're a lot less bright, and also in this case the ionization equilibrium, unlike the prominence material, are only in ionization equilibrium between 1.2 and about 1.5 for most of these lines. Okay, so as I mentioned, we looked at several different lines. We tested a lot of different lines, but we also included a list of recommended lines. And so the recommended lines are any line, this is sort of very arbitrary, but any line that reached a value above an intensity of 1 at any point during the evolution. So it's actually really important to actually go and look at these plots because the line may not be visible throughout the entire evolution of the plasma, but maybe, especially with something like the PCTR, which is already very, very dim, right? The intensities might only be observable during a particular stage of the evolution. So I went through so from the 118 lines, there are 70 lines that were in the recommended list. So I went through and I looked and I picked some of the lines that might be useful for density and temperature diagnostics. So this is for the prominence plasma, and like I said, there's a ton of them in the list, but I just chose a few. So for the prominence plasma, of course, it's important to keep in mind, especially for the prominence, that some of the lines might be optically thick. So it'd be really important to check that, but may become less and less important as the plasma begins to expand and the density decreases, right? So this is just a list of several ratios that I included that are are fairly bright in the prominence material. Some of them may be observable with SPICE, some of them may not be. And the ones that I highlighted in orange are there are ions that remain in equilibrium out to 2 solar radii, so throughout the evolution of the plasma. But even if the ion is out of equilibrium, that they're still useful, right? So if you have a ratio of the same ion, in this case, the relative abundance, a lot of that information cancels out, so they're still useful for diagnostics. So with UCOMP, obviously the two coolest lines, the hydrogen and the helium line, are going to be very important for studying the prominence evolution in the corona, primarily the H alpha, which is a lot brighter than the helium line. And so there's a ton of DECUS lines that are also going to be that are very bright and very observable in prominence plasma. And so this is just an example of two lines, the calcium 2 and the H beta, that have previously been used for pressure diagnostics of filaments on the surface. That may also be applicable throughout the evolution, right during the eruption as well, since they remain in equilibrium. But of course, with DECUS, it's not going to be looking very far off limb. So this may be not so important out in the corona, but it still could be important for studying these properties during the initiation and liftoff of the material from the sun. So still important. And so for the coronal plasma, there are several consecutive lines of iron that might be useful for looking, either looking at the evolution of hotter plasma or the heating itself so the lines range in formation temperature between 1 and just over 2 megakelvin. And so all of these lines that I'm including here, there's another argon line, which is fairly bright as well in this component that samples even hotter plasma. All of these lines are going to be observable with UCOMP. So these are all the lines. These are all 9 lines that are going to be observable once UCOMP becomes operational. But there's also some lines that are overlapping with cryo-inertia on DECUS that may be useful to use together. So if you were lucky enough where you did see a CME with cryo-inertia and UCOMP, and they were both looking in the right direction, well, UCOMP is going to be looking at the entire corona, you could theoretically study the release and the evolution of the plasma out to 2 solar radii, which would be good to study the heating and things like that. There's also a silicon-10 line that's going to be observed by cryo-inertia that also is relatively bright for this component. Okay, and so this is just a summary to wrap up everything. So this is the table that I was talking about of the recommended lines that we included in the paper. So there's 70 of them. So what we include is information about the line and also which component you're most likely to observe that particular line. And so generally what we find for the different components is that, so for the prominence material, the signals tend to be a lot brighter than the other components. So they're able to maintain a really strong signal out to 2 solar radii while remaining in equilibrium. The intensities that are formed in the strongly heated tenuous PCTR, this plasma, are a lot more transient, where there's only a limited time during the evolution of the plasma where you can actually where these lights become bright, and so many of the lines peak and dim following the rapid creation and immediate destruction of the ion. And most of them this is happening very far from equilibrium as well. For the coronal component, most of the lines are going to be best observed closest to the sun, where all the lines are brightest, and most of the ions are in equilibrium at that particular height. And so all of these components that we looked at can be studied with different instruments. And so theoretically, you can combine all the observations from these different instruments to study CME plasma. And if you're really lucky, you would be able, if you're really lucky to observe a CME at the sun and also have it be observed by Parker Solar Probe and Solar Orbiter in the heliosphere, you can also connect some of those observations to in situ properties of the plasma. And so I think that's all. That's all I have for you guys. Thank you.
Any questions? Sarah.
So, UCOMP, when UCOMP comes online, what would be the first thing that you would want to observe with it?
Well, so I'm here because I wanted to observe CMEs. And UCOMP is really useful in that sense because it has such a large temperature range of the different lines. So what you want to do, so after the study, what I'm going to use it for is essentially look through the lines and see if we can figure out a sequence for a use case. So if we do see a possible eruption, then we can sort of start the sequence to look for CMEs. Like I said, I'm interested in the heating and how this plasma is evolving in that way. So I want to calculate an energy budget. So it's important to not only look at the prominence, but the entire CME, which I think is going to be very doable with all of these lines. That's how I want to use UCOMP.
Since you're very interested in the energy budget, and I also. So my question is, based either on your work or what other people do, does the heating go primarily into kinetic energy, or into expansion, or into thermal emission,
So
or
the
some part conduction?
yeah.
Four possibilities.
So for the paper where we looked at that CME, where we reconstructed that CME, so we took it a step further where we calculated all of those things. So a lot of people, through observations, have calculated the kinetic energy, the thermal energy, and the potential energy seem to be very similar, very important. And that's sort of where all the energy is going.
And
The-
also expansion.
Yes, so expansion, and I can't remember what thermal conduction looked like, but I know that the thermal energy, kinetic energy, potential energy are probably the three most important, based on the calculations that we did with this CME. There's a lot of
I've
yeah.
seen estimates that say that most of the energy goes into kinetic energy.
Mhm.
Most of the heating goes into kinetic energy. You're saying it's
Huh.
sort of equal precision.
Well, it also depends on what CME you're looking at, because they can vary a lot, which is one of the reasons why I wanted to show that particular eruption, because some of them, I mean, they can be a lot more energetic, and so a lot of this energy, right, can be put into different things, and also different components. So one of the other things that we found when we calculated these terms for each plasma component, we saw that most of the thermal energy was going towards heating the prominence. So it's being transported into that particular structure of the CME.
So I have a question.
Mhm.
Some of the interesting lines that you predicted or you showed in the table are already observable with previous instruments like SUMR or CDS or whatever.
Mhm.
So what do the new instruments give us that these older ones didn't? Is it that they can show us like a wider parameter range of temperatures or densities, or are they seeing different? Is it a resolution better, or is it they can see different parts of the corona, or?
That's a really good question. I actually don't know. I'm putting out there just for, I guess, knowledge of which instruments are going to be capable of looking at particular lines. I really didn't go into that. Depending on what you care about and what you're studying about the CME, that will come into play, I think. Is Sumer still? It's still.
Well, SUMR does no.
Yeah. So that's another thing, right? So you're not, I mean, in this case, it's not going to matter because SPICE isn't looking at this line, but some of the lines, some of the spectrometers aren't looking at the sun anymore or aren't operational. This may be useful to have like another instrument that might be. It's also really tricky with SPICE because it's not going to be sitting at like L1 or something. It's going to be moving around, getting closer and farther from the sun. So that's also another tricky thing that I don't know how people are going to deal with.
Anyone else?
I also have another eruption if you want to look at it. This one takes a little bit longer, but it's happening. Yeah. You could see all the plasma and absorption first, and you can see the heating happening, which is really cool. They all sort of light up in different colors, different EUV channels.